All right. Good morning, everybody. Happy Monday morning, bright and early, 8:30. Um, so for today's class, let's see where I last left off. I believe I was going over threads last time. I went over a few simple examples involving threads. So I guess for today's class, I will continue from that point. So I'm going to just resume on threads. And there's a new assignment posted, which is basically just a program involving threads. So I'll go ahead and discuss that as well. And if we have some time, then I'll go over the next sort of data structure, which will be binary trees. Let's go ahead and just first begin with a screen share. There it is. And see. Yes, this lecture is being recorded. Yep. I post all the lectures up onto my YouTube channel, which is linked on my Discord, the announcements area, pinned over there. Let's see. We can find that thread file. I can always create a new one, I guess, in the worst case. Let me take a look. Hmm. I think it's over on this screen, my mistake. I think it's over here somewhere. Hold on. Oh, there it is. Okay, cool. Oh, look at me go to my Discord and check it out then. Hang on. Oh, I think somebody already sent it. So, okay, we're good then. All right. So from last time, we had this thread program. We had T1 and T2 created. So remember how a thread works? It just spawns some type. So when I say thread T1, it spawns a thread T1. And for every thread function, we have to pass in, well, first you have to, well, sorry, not thread function, thread constructor, because right now on line 13, we are going to spawn a thread, which means we're going to create a thread using a thread constructor. And for the constructor, we have to, of course, pass in, well, the function name. In this case, I'm passing in foo. So I'm saying, okay, thread T1, I spawned you, go ahead and run the function foo. And then this is the parameter I want to pass into that function foo. So basically, thread T1 is going to get spawned. It's going to run the function foo with that parameter hello world. When I say thread T2, it spawns another Mr. Meeseeks character, if you want to think of it like that, and I pass in the function foo once again, but with this parameter. So it's going to go ahead and spawn a thread T2, Mr. Meeseeks, go ahead and run the foo function with that parameter, Bonjour le monde, the French version of Hello World. And of course, when they're spawning right here in main, if I write any code in line 15, this actually would run in parallel with the threads because right now the threads could be running, but when we have this part here, t1.join, t2.join, that basically implies that we're waiting for two threads to stop because whenever you're doing thread programs, you want to always make sure that we sync up with our threads. We wait there until our threads are both done. So here, waiting for T1 to stop. So right now, our main will be waiting. And when T1 is done, okay, move on to the next line. It waits there. If T2 is done, okay, now at this point in our code, line 18 and beyond, now we can guarantee that thread T1, T2 are done. So now there is nothing going on at the same time. So basically, a thread spawn, and a thread will run its code, but there's no knowing what speed it will finish. We don't know if T1 will finish first or T2, but this syncing up part, we just want to wait until both threads are both just done. We don't really care which one's finished first, but as long as T1 is done, then T2, okay, we can move on with our program inside of int main. And then we have this void foo function here, which outputs msg. And we used this mutex tlock earlier because the whole idea was that cout is a shared variable among these two threads, T1 and T2. So if they're both trying to output at the same time, then there's a chance that, well, the outputs might be a little bit out of whack. So imagine, let's say we have two Mr. Meeseekses trying to write. Let's say cout was like a piece of paper, and they're both trying to write that piece of paper. So imagine what happens. One thread is writing, one Mr. B6 is writing Hello. Other thread sort of comes in and kicks that thread off and starts writing Bonjo. So bonjour. And other thread comes back, so there's going to be some competition going on between the two threads. So you want to make sure you don't have this competition. So this locking mechanism will allow only one thread to write. Now, this is actually a very bad use of threads, but we want to make sure we lock certain parts of our code to make sure that only one thread can access that part of our program. So let's go ahead now and do some more stuff with threads. I'm going to open up my terminal so I can compile stuff. Okay, cool. Go to my desktop. Here. What's going on? Okay, try this. This is weird. Oh, so that's why. Okay. All right. Mount C drive. Awesome. Perfect. There we go. I'll make this a little larger as well. So let's go ahead and create another file. I'm going to create one called threads02.cpp. All right. Let's see. Where is this file in our desktop? Where's Waldo? Uh, this is always fun trying to find where is it. It creates a file in some random place. There it is. All right, so once again, we're going to write this program. So we have to have IO stream as always. I'm going to use a vector on this one. We'll see in a second how it's going to work. I guess I'll include string just in case. I don't think I'm going to use string in this file, but why not? I'll definitely use a mutex, so I'll definitely include that as well. I think that's all I have to include in this program. Of course, increase std. So in this program, return 0, very important for code gray, returning 0. So this program, I'm going to actually compute various amount of factorials. So 1 factorial, 2 factorial, but we'll do them in parallel. That's the idea. I'm going to create a function called void factorial, and then I guess I'll just maybe use int n. It's my parameter. So void factorial int n. And I guess I'll create an unsigned long result R, because this might get pretty large, so we're going to make sure that it's not going to mess up our sort of variables. So this way, no overflow will happen in this case. So obviously, to compute a factorial, it's just going to be int I equals 1, I less than equal to n, I plus plus, and then R equals R times I. That's standard factorial function. Then I'll have my cout, and then I'll say n factorial equals that result and L. And I guess I'll return the function. Okay. So here's our factorial code. So in this program, I'm going to actually use an array of threads, or actually a vector of threads. So let's go ahead and do that. So I'm going to spawn maybe 10 threads and have each one compute a factorial. Let's see how we actually do this. So vector, thread, and I'll call it thread pool, although this is not really an actual real thread pool in a sense, but I'll call it that. So we create a vector of threads. So, I mean, a pointer type can be used as well for this, but it's going to be a lot more confusing. So I'd rather just use a vector instead, because a vector makes this entire process a bit simpler. So let's go ahead and spawn 10 threads and pass in a different sort of n value into each thread to compute each factorial in parallel. So I'm going to go ahead and say, so for int I equals 1, I less than equal to 10, I plus plus, I'm going to say thread pool dot push back. So remember, the pushback function is our standard method of inserting something to the back of our vector. And I'm not going to, push back integer or a double or anything like that. I'm going to push back a thread. So let's go ahead and do this. Let's try to make sense of what this code actually does. So when I say this right there, this thread factorial I, which I just highlighted, I do that. Well, that's going to spawn a thread. It has no name, but it's okay because we're going to insert that into our vector. So right there, I just spawned a thread using a constructor, and I passed in a factorial function into this thread. So it's going to run that factorial function, that thread. And I'm going to pass in I. So for that factorial function for that thread, that end value is going to be whatever I passed in as I. Then it's going to run that thread and put it into the vector. And then next sort of instance of this loop, it will again spawn another thread, and it'll pass in a different I parameter into that thread. So it'll first spawn 1 factorial, then 2 factorial, then 3 factorial, and so forth. It'll spawn them all one by one. And you push them onto the vector, so we know that thread pool index 0 is our first thread. Thread pool index 1 is our second thread. So we definitely can ID these threads. Instead of using a variable name like the last example at T1, T2, well, thread pool 0 is going to be our first thread. Thread pool index 1 is our second thread, and so forth. So that's going to spawn our 10 threads, and they're going to run in parallel. So we spawn them one by one. Once they're all spawned, they're just going to run in parallel, and just like we just spawn 10 mission meseekses, and they're going to all independently run their factorial functions. So now you want to make sure you want to wait for them all to be done before you move on to the program. So I'm going to have a loop. So for int I equals 0, I less than thread pool dot size I plus plus, then just say thread pool index I dot join. So we're going to wait for every thread to stop. So we're going to first wait for thread 0 to stop, then thread pool 1 to stop, then thread pool index 2 to stop. So waiting for all of them to stop first before we move on with our code. In this case here, I'll just maybe put a cout statement here to say cout all done. This is going to be written once all the threads are done. So this is going to be our code. And I will see right here why mutex lock can be relatively good to use. So right now, this cout statement, this is going to cause a little bit of strange output. But let's go ahead and just run this and see what it does. So of course, G++, and then pthread, then threads, I think it's called thread 0, 2. Okay, now once again, if you're on a Mac, you don't have to include -pthread, but you do have to use dash std equals C++11. I do have that linked, I do have that in the PDF of the assignments, so you have that there in case if you forget. But for the next base system, you have to include pthread, like that, in order for it to compile. What's going on over here? Oh, got to include thread, the most important, library, and have all this other stuff included, but not thread. Okay, so now it should be okay. Okay, so let's go ahead and run this. And there we go, race condition at its finest. Yes, so the mutex lock is for locking, because look at this. This really came out very bizarre, because one thread was writing, and the other thread took over and wrote, so we had these 10 threads all at the same time trying to cout, which caused all kinds of chaos right there, because, well, we don't want to have, because cout is our shared variable in this case. So they're all using that same cout variable, so that's a problem. Let's run this again. And now it's a little different again. So you can see every time it runs, it's a little different because there's no really guaranteeing what speeds they will run at. The threads have different speeds and different orders when they finish. So they're all trying to write at the same time, and it creates all that really bizarre output. So this is where having mutex lock is very nice because we can sort of allow only one thread to write. Now, I'm going to go ahead and just create this variable mutex. I'll call it tlock again, just because. So for thread lock, I guess is sort of what tlock really stands for. And now one thing you could do, you could say tlock.lock right there, and then tlock.unlock right there. Now, if you do something like this, it's going to output it sequentially, but if you do this, we're really defeating the purpose of having threads because, well, we want to put that lock only around parts of the code that we want to have it definitely be sequential. So in this case, well, each thread can easily compute its factorial value in parallel, but only the output part is really, we want that to be really done kind of sequentially. So always be sure to always make sure you lock the correct parts of your program. I mean, it'll still work, but then you're not taking advantage of threads. You want to, the whole point of threads is that we're computing these 10 different factorials in parallel. So this part right there, each thread will do this part in its own. So think of Mr. Meeseeks. Each one is kind of, using a calculator and computing its own factorial. That can be done easily in parallel, but then when they're going to write, we want to make sure each one writes their own value. But while one's writing, other threads have to wait while one of them is writing. Once it's done writing, it'll unlock and another thread can actually get in. So what happens is when one thread hits this line, it gets the token. And what happens, other threads are going to be sitting there waiting while this one thread's writing. Once it writes, it unlocks, and then one thread can enter. So only one thread at one time can enter. The idea. Other ones have to sit there and wait until the thread is done and unlocks. Now, if you forget to unlock, which I'll show you in a second, then our program will deadlock if you forget to do this, but we'll see in a second what happens then. But anyway, let's go ahead and compile this now. And now it outputs nicely, but notice that we have first 1 factorial, then 7 factorial, then 3, and then, so we saw the order was not always 1 to 10. But the idea was that once one of them began writing, only one was able to write, not all 10 at one time trying to write. So let's go ahead and now and just run this again. We see here orders every time is a little different. It's not always the same order. But the idea is it's okay because we don't expect it to be in the same order. We just want it where we don't try to write at the same time to see out. That's sort of our idea, really. Now, once again, let me just sort of just comment this part out. Let's see. Yes, so the locking only controls, in this situation, we only have it wrapped around the output. So each one will compute its value correctly, but when trying to output, then only one thread can output. So everything is still running concurrently. This is all running in parallel. This part, each thread is doing its own parallel computation, but when output is happening, only one thread at one time can output, which is what we want it to do. Otherwise, it's going to cause all kinds of issues. Race conditions are definitely a big problem involving threads, but you'll learn about that probably more in your OS class. You'll learn a lot more details of this, but it's just like a little simple little crash course on threading and multiprocessor stuff. Now in this case here, I forgot to unlock. So that happens, well, we're sitting there. Our program then deadlocks because what happens is one thread does not ever unlock, so other thread's going to sit here and wait forever because no thread will ever be able to get to this part of our code. So think of locking and unlocking really as like going to the doctor's office and only one thread can get into the door, then the door locks. When a thread leaves, the thread walks out, unlocks the door, another thread walks in. This is almost the same thing as saying, well, okay, the patient or Meeseeks sort of enters the doctor's office and sort of jumps out the window afterwards. And then what happens is, well, okay, the other threads don't know that because the door was locked. So they're kind of assuming that this thread's still, still getting sort of help from the doctor. So it's they're waiting. They have no idea that the thread is gone because the thread wasn't really nice enough to first unlock before it leaves. This critical section of our code. Let me go ahead and close this word. So yeah, it's kind of like another example right there. Now, of course, if I want to spawn more threads, after all, I still could spawn more threads. Let's go ahead and do a program where we spawn more threads after this. So after we're done with this part, we join all of our threads. I'm going to spawn more, but I'm going to first do the following. I'm going to say thread pool dot clear. And I'm trying to think of an analogy for this, but it's very morbid. So I'm going to try to make it not so morbid. So in this case, we join all those threads. So thread pool 0, thread pool 1, all of them, it's taking up space in our thread pool. So it's a bunch of threads that are no longer running or alive at this point. So we don't want to really work on thread pool index 0 or index 1 because those are just thread um, remains, I guess, if you will. So you want to clear thread pool out if you want to spawn more threads. So that's what we have to do because otherwise we're going to try to join. Let's say you try to join thread pool 0, it's going to cause an issue. Now, of course, we could sort of begin joining from index 10 and beyond, but this is a lot more simpler. We just sort of clear the thread pool out. We deallocate all those elements. So that way we're not going to try to join a non-existing thread. I'm going to go ahead and just sort of copy and paste all of this to spawn more threads. So I'll go from maybe from, let's say, 11 to 22. Let's go ahead and run this again. So here was the rest of the threads we spawned. I guess this is also a little bit out of order because we first had 14, then 18, then 16. So we see that the order was a little bit off, but it's okay. And we know that, I guess, I told you earlier, so now we can see it in action that the thread speeds are, we can't really determine which will finish first or second, but all we care is that they're going to run and we want them to sort of do some work in parallel. So that's the idea with how we create multiple threads like this. Now, um, let's see. Oh yeah, so another sort of, how should I say, another topic involving threads is, well, how many threads can you spawn at one time on a machine? That's a good question to ask. So what is that value? Well, it depends on how many cores your CPU has. So I believe each core can be broken up into two logical cores. So basically, it's twice your core count. So I believe on my processor, I have 8 cores, so 16 threads can run. But of course, this program might run on different, sorts of computers. So you want to make sure that if you do want to, because the idea here is, okay, so I'm going to first just do this, then we'll go ahead and I'll show us some examples. So anyway, I'm going to call this variable max threads equals thread hardware concurrency. So what this function does is it retrieves the amount of threads that can be run on the system you're running this program on. So this way, if you have this max threads, which I'll make this lowercase h over there, is you can actually have your program scalable on different hardwares, different processors. So this way, if you want to, kind of cap how many threads you want to spawn at one time, those variable max threads can be used to sort of make sure we don't overspawn on our system. Now, we'll go over what happens if you overspawn, but for now, let's go ahead and just simply cout this variable, max threads. I want to know what's the amount on this system. So it should be 16, but just, double check this, I guess. And that number up top, 16. So yes, this particular CPU can spawn 16 threads concurrently. So it can run 16 threads in parallel. It can't run more than 16 in parallel, obviously. But what if I were to actually spawn, maybe I'll go ahead now, you'll comment this part out for right now. Just don't have, I'll worry about this. Let's go ahead and spawn 21 or yeah, 21 threads right now in our code. Let's spawn 21 threads. Let's see what happens if I try to spawn more than 16. What's going to happen? Well, I mean, it worked. If you see here, it's same idea. We have our threads outputting. They're out of order a bit, but it definitely worked. There was no errors. So, well, how is this possible? How can we spawn more than 16 threads if we know that it can't run more than 16 at one time? Well, the operating system comes into play here. So the operating system will go ahead and manage these threads. So trying to spawn 21 threads on a 16, sort of max 16 system, what it will do is at any given time, 16 threads will run and 5 threads will be in timeout mode. And then the OS will, every now and then, using maybe a round robins based system, it will randomly or based on some order, it will take one thread's running and put it back in timeout mode and swap a timeout mode thread into running mode. So it's going to kind of manage all those threads and try to manage or try to simulate this multi-processor type of situation. So the operating system is sort of swapping threads in and out basically, which is going to slow down your process, but it will at least be able to emulate 21 parallel threads. So I guess really you want to try to avoid spawning more than your max threads amount, because if you do more than that, you're not really taking advantage anymore. Now your program will start slowing down because the OS is taking a lot of time swapping things around. Let's take a look at the question here. Yeah, if you spawn more threads than your CPU can handle, it will have a little bit of a slowdown actually, because doing extra swapping work by the operating system is going to actually take up more time. So it's wasting time doing that. So you're getting a little bit of a slowdown actually. So it'll work, but you're not really taking advantage of your, I mean, you are, but you aren't really. Having more threads does not make the problem faster. So there's actually definitely so having always more threads is not going to always solve the problem but make it faster. It depends on one, how many threads your system can actually run at one time, and two, um, also depends on, because every single program that does some type of multiprocessor type of work, not every single part of this can be done in parallel. Notice this factorial function. This part was done in parallel, but this portion cannot be done in parallel or else it will have some issue. So there's always going to be some parts of your program, well, not always, but typically there'll be some parts of your program where it's not going to be able to completely parallelize it. So if there's certain parts of your code that can't run in parallel, then at a certain point, more processors or more threads, even if they can run in parallel, it doesn't matter. It's going to not cause a speed up. Let's say if your system can run unlimited number of threads in parallel, but there's certain parts of your code that can't be done in parallel. That means at a certain point, more threads is not going to cause a speed up anymore. That's actually, I believe, Amdahl's law, which I'm not really a big hardware person. I mean, I guess I can build a PC, but I mean, anybody can do that, though. Just, you have your parts, you put it together. Of course, there's a lot of screaming and shouting and getting angry because that thing won't go in there and the screw fell right there, and now you're really upset. But really, it's not really hard. It's just frustrating to build a PC. But I'm not a big systems or hardware guy, but there's a rule that if certain parts of your code can be parallelized, adding more processors or threads to the problem is not going to cause a speed up anymore. So I can make more analogies about that, but I'm not going to because this is a CS course and there's nothing, and I can make any more analogies about that. But anyway, um, so yeah, it's basically the crash course on threads. So now, just to kind of talk about this right now, if let's say I want to be able to do 21 different threads, so the real better way, or this way is not going to be much better either, but if you don't want to spawn more than 16 threads at one time, exactly. That's actually a good analogy. I like that. So the question here is adding, yeah, so not question, but the comment here is adding more lanes to the highway won't help if there is only one exit. That's a fantastic analogy to this. It's actually a good analogy. So definitely, so I'm happy I said yeah, that's definitely the best way to think about this. So if there's certain parts that only can be done in series, not in parallel, then having more lanes is not going to help, or more threads is not going to help. So perfect. So I like how we're all on the same page on this, or at least it seems like we're on the same page. I can't see everybody, but I think we're on the same page. So that's important. Um, so if let's say you want to, in fact, let's say right now I'm going to spawn 21 threads like this. So what you could also do is you could actually only spawn 16 threads at a time and then join those 16 threads and spawn 5 more. So in this loop, you can have a condition that checks if let's say your thread pool size is equal to max threads, then don't spawn any more threads. Instead, wait for them to join. So have a loop that joins all those threads, and then clear that thread pool out, and then spawn more. Yeah, maybe I'll write this code here just to kind of give us an idea. So this way is also bad because to sort of sync with threads, then spawn more threads is not really also because the spawn a thread also takes up CPU time as well. But at least this way you're not spawning more threads, but here's another option. So if I say if thread pool dot size modded by max threads equals 0. If that's the case, that means we already overspawned for our system. So we go ahead and have a loop right there and just say, actually, I'll put this in a bracket. We have a loop, so for int I equals 0, I less than thread pool dot size I plus plus thread pool I dot join. And then we go ahead and clear the thread pool out like that. So at least what happens here is we never allow our system to spawn more than 16 threads at a time. So we're doing over here this condition here. If we already have 16 threads currently spawned, we're going to wait for them to all finish first. When they're all done, okay, now spawn more threads. And this part right here is gonna join any more leftover threads because maybe we don't have exactly 16 right here. 21 is being spawned. Then there's 5 more threads that's going to be running, and this loop will terminate. But there's 5 more threads still running. So this will just kind of wait to join any leftover threads that are still possibly running after this loop. But really, we're only spawning 16 at a time, basically. That's what this if statement really checks for. You don't spawn more. This is not really more efficient, really, but if let's say you don't want to spawn more than max threads amount, then this if statement right there kind of doesn't allow your code to spawn more threads if that was an issue. So it still works. So it first spawned 16 threads in parallel, and after 16 was spawned, then the last 5 was spawned in a second round, I guess, if you will. So yeah, so I guess I'll go ahead now just post all of this code up onto Canvas as well, so we have access to it. But anyway, that's kind of my quick crash course. Now, also I could have covered that you can have a thread spawn another thread as well. So T1 can spawn another thread T2, but that's not going to be really important for right now. Although for a thing for operating systems, you often have to sort of create child processes. You will do something along those lines, but we'll just go ahead and keep it like this for right now. So spawning multiple threads like this is going to be useful in a vector fashion. So any questions on this? I don't see any questions popping up, so I'm guessing we are okay for right now. I see a question. You might be able to sort of output them in order. I mean, you have to do other types of work, but I guess it's not really important. So because the idea is that when threads finish in different orders, somewhere in main we're going to kind of filter it out. So for example, if instead of just outputting the value, we could just push sort of, let's say for example, we want to do 16 or we want to do 1 factorial to 16 factorial in that range. I can create a vector that has 16 elements. Each thread is going to insert its result into an index of our vector in different orders. And in main, we can go ahead and output it in the right order, if that makes any sense. So the main will be our like our sort of our thread that's going to manage everything. So of course we could have them insert into a vector in different orders, but it'll give us the final results, and then we can just have main output them in a loop like that. Well, it depends. So it has to have big enough sort of value, a big enough problem you have to have essentially to have any kind of real runtime increase. So now, asymptotically, there is actual maybe content in the later on CS course that goes over a class of problems that can be done. I think in hold on, pseudo-logarithmic runtime you can get if you have multi-threaded problems like that. You can do sort of analysis of algorithms like that, but we're not going to worry about that. But the runtime is going to improve, especially for big input size, and if you have a lot of threads we can use. So theoretically, it should cause a runtime increase, but it has to be a big enough problem and a big enough number of threads to make this work. So, and also for certain problems that we have some disjoint problems with each other. We have some sorts of so I guess the idea is that it depends. So it's not going to always guarantee a better runtime, but it depends on the problem. So big enough input size, enough number of threads. And of course, a lot of times with threads, you want to run them on GPUs instead because you have a lot more cores on a GPU. So that's why for games and everything, threads are kind of popular because a GPU can run has a lot of cores basically. So, but for small input size, yeah, we won't see a big difference really. So anyway, that's that I think. So I guess I'll go over the assignment 4 now, unless I have any more other questions here. I don't seem to have any at the moment, but of course you can ask it while I'm sort of going to display this. Assignment 4, of course, the dark theme is what we're going to go with. And screens, let's put it there. There we go. We have Mr. Meeseeks there, so he will be helping us out with this assignment. So we're going to basically write a program that's going to compute a multiplication of two numbers. So now in this program, we're going to be using potentially numbers that are very big that might not be storable into a typical unsigned long or whatnot. So a vector is going to be maintained to store these numbers. So consider these two numbers here, number 1, number 2. These will both be two vectors of type short or of type int, doesn't really matter, but I guess short is because each will be only one digit, so there's no need to have integers for each element, but it wouldn't really cause a big problem either way. So we have these numbers here. So we're going to have to implement basically this second grade or elementary school long multiplication. Remember how that worked? Well, I mean, let's go ahead and recap this if in case you forgot, but the way it would work is this number 1. So we're multiplying number 1 with number 2. So using a loop, multiply this to that digit, then to this digit, then to this digit, and so forth, right? And we're going to store its partial results somewhere. So after you do also apply 1 to the 4, then to the 2, and the 5, and 1, we're going to store those digits into another vector. So we'll create another vector over here, this, and it will contain 4, 2, 5, and so forth, right? That's sort of the grade school multiplication. Yeah, so who would have thought? I guess here is an example of life. You have to go backwards in order to go forward in life. I don't know why I said that. It's a very terrible, how should I say, a very terrible quote. But we are in fact going backwards to go forward. Yeah, that's definitely the message. That's whatever that is. There we go. But that's the deal here. So now we're multiplying. Now next time I'm gonna multiply the 6 to this digit, then 6 multiply it to. So maybe I'll circle this instead of just So multiplying this digit 6 to the 4, then 6 multiplied by 2, and then by 5. We're doing that work, right? Grade school multiplication. So in this case, over here, we have a 0. Then we're going to have 4, Then we're going to carry over to 2. So we're going to have, so we have 6 times 4 is 24, where we carry the 2. And then we're going to have 6 times 12, which will be 6 times 2 is 12, plus the 2. So it's going to be 14 again. Carry over the 1, and so forth. So we're going to go ahead and compute all these partial results. So remember, we're going to have a lot of these. So we're going to have, 0, 0, and we're going to have, so we're going to have all these partial results. So remember that from second grade. I know it's been a while. I mean, we're not second grade anymore, but we're grade school multiplication. This is a long time ago we learned this, but, hopefully it's not hard, but coding this, though, is definitely going to be a pain in the, well, it's a pain in the neck, I guess, to code this, but the concept, though, is very simple. To create these partial results, they're going to have to go ahead and add up these partial results at the end. And so forth. We have to add all these up to get our result. That's really all there is to this. So very simple, right? We're doing second grade math. I mean, how hard can this program possibly be then? I mean, this can't be a hard program for doing second grade math, right? Anyway, so here's the deal. So, okay, so we know how this works by using this grade school multiplication, but I want to go ahead and do this in parallel. So, for example, if I'm multiplying 1, this digit, to all of these digits right there, let's say, and then subsequently, I multiply this digit with all of these as well, the question is, can I do this in parallel? And the answer is absolutely. Because, okay, we're having that number 1, number 2 as a shared variable, yes, but we're not writing, we're just reading from those variables. So 2 threads at the same time can read index 6 and 5 and 4 from this number. That will not cause a problem. A race condition in general is only an issue when we're trying to write that same shared variable. But now we're just simply just reading this variable. So I can multiply 6 to these digits at the same time multiplying 1 to those digits, right? I mean, there's no rule that I can't do that. So I can create 2 threads that can do that. And of course, what if I create another thread? I can create one more, this will be in green. This can multiply to all these also. It's almost like a Pink Floyd album right there, all these really crazy colors right there. But anyway, yes, that's the idea. So we can do those in parallel, no problem. That's not going to cause any issue. So, got to figure out a way for how we can actually do this. So for this program, you can have all your vectors, like number 1, number 2, as global. These can be global because passing a reference into a thread function is going to cause problems. So make sure there's number 1, number 2, make sure those 2 vectors are simply global. And we only have to pass in indices. So let's say thread, you go ahead and I'm going to assign you index 5. And this other thread, I'm going to assign you index 4. In this thread, I'm going to assign you index 3, and so forth. So you assign every thread an index of number 2 that I'm going to use and multiply everything in number 1. So let's just have number 1, number 2 both be global vectors. So global is the one time where globals are going to be okay. So make sure it's a global variable, so that way it can sort of, each thread will be able to access number 1 and number 2. You just pass in an index telling the thread which index of number 2 multiplies to number 1. So these partial results, well, this is going to actually be a 2-dimensional vector. It's going to be a 2D vector. Because you have to have all these partial results stored. So we're going to push an entire vector, a 1-dimensional vector, is pushed onto this. So we're going to push a vector 1 by 1. So each of these results, it creates a 1D vector for its partial result, and this vector is going to be a 2D vector. So you actually can push an entire vector into a 2D vector. It's going to add that whole entire row. Now this has to be done in sequence because two threads at the same time try to push into this vector, bad things will happen. So this part we have to use a mutex lock on this. So I'll put this here, mutex lock. Because otherwise, if there's two threads at the same time trying to push onto this two-dimensional vector, I guarantee it's going to cause a problem. So while one's being pushed, other one's being pushed at the same time, and it's going to be just, I mean, craziness basically what happens. You want to make sure you lock, push the result onto this vector, unlock. So every single thread will have its own individual 1D vector that's going to be the result of multiplying this one digit to all of these digits. It stores that partial result in the order in which we sort of insert them into this vector does not matter because we're going to add up anyway. So the order in which we have these solved, I mean, I could have solved this middle of a value first and then solve this. It doesn't matter what order we solve these in. As long as all these partial results are pushed onto this vector, we're good to go. Then of course, now we have to implement long addition, which is another sort of task within itself. But that part will be done in sequence. It will be done in main. So in main, you spawn your threads. Each thread will compute its own partial result. When they're all joined, all done, then in main, just have a sequential function that's going to just add up these results in sequence. You don't have to do them in parallel because that part, you kind of need to do that in sequence. You can't really do it. I mean, you can do it in parallel, but it would be a little complicated. So you can do that part in sequence. But that's really all there is to this program. So make sure these two vectors are global. So make them as global vectors. And this 2D vector will also be global. So the only thing that pass into each function is passing the function name into the thread constructor, and then pass in which index of number 2 you want to actually multiply to everything in number 1. So just passing one integer. So passing the function and then comma that one integer, telling that thread which one to multiply. Let me see. I think that's kind of like the idea for right now. This actually has a typo, I think, here, except you will multiply. So let's see. I think there was a typo here, but this kind of explains the whole concept, though. So anyway, I can probably save this actually and sort of put this up onto Canvas as well. But yeah, so I think I kind of, yeah, this is actually this whole paragraph here sort of summarizes all of this I just did right there. So that's that. Um, so anyway, for specifications, comment your code, and also, this part here. So make sure you don't spawn more threads than you can handle. I guess we're going to try to give the operating system a little break and not have it do too much work. So using the method I sort of showed you, try to make sure you don't spawn more. So I guess if you spawn more, it won't be, maybe it'll be a very small error. It won't be like, I'm not gonna maybe have us take off too much points for this, or maybe, well, it won't be too much points taken off if you do, but try to, make sure to get 100%, try to just not spawn more than the hardware concurrency function gives you. And also, make sure the output has all leading zeros removed. Now, oh yeah, just to kind of go back up here again. So in this situation, you want to make sure for this addition part, so knowing the size of number 1, number 2, you know how big the max number of digits you can have for your partial sums. So you can add leading zeros to some of these to make sure all their place values align up perfectly. So remember, we have a 5-digit number and a 7-digit number, so we know basically what's the max amount. Then I think we just add up the size of number 1, number 2. So each of these vectors should be size 12. So then what you have to do is if one of them only gives you 3 digits, then add 9 zeros to the front to make sure these numbers all align up nicely when you're trying to add up your partial results. Let's see, so question here. So do we have to use a 2D vector for the result? Couldn't we just calculate the value of each multiplication and just multi multiply it by 10 place and add it up. Yeah, but the problem is, I guess if you store the partial, I guess what you could have like a just a one vector that stores the partial results, the current partial results, and then you have to just add yours to that current running one. I guess if you want to do like that, you can. So yeah, that's I did it like this. So I didn't mind more drawn up. Mine was I did mine more like separate the parallel all that, but I didn't think about that. But that's actually a good idea. So you can just have one vector, a a C vector, a result vector, and you constantly add when each thread is sort of done its work, it will add to that result. Yeah, that actually definitely will work. So instead of having all these partial results at the end, add them all up. You just add them as you go. To have one vector just sort of stores the current result, and every thread's done, it'll add it to that current result before the thread will finish. Yeah, that actually would work. It's a pretty good idea, actually. So, yeah. So I guess either way is working. This way I kind of outlined like this, but either method works. As long as you do this multiplication part in parallel is sort of the real, that's really the sort of the meat of this program really is just sort of making sure you do that, I suppose. So make sure you just, do this part in parallel. And here we go, here in big capital letters in red. What do you mean by parallels? Well, in this way, what I said right now is that you want to multiply these in parallel. So we're doing a grade school multiplication. You do is you take this number 1, multiply it to 4, multiply it to 2, multiply it to 5, to 1, to 6, and then you store that result. And then you do 6, multiply it to 4, 6 multiply it to 2, and so forth. But you want to do this in parallel. So instead of doing it one by one, you can spawn 3 threads at once, and one thread will multiply 1 to all of these, and then 6 multiplies to all of these, and 7 multiplies to all of these, and you can do them all in parallel. You don't have to have it, you can have 3 threads at one time doing that work. Cool. Yep, no problem. So the big sort of red letters, of course, make sure your output has leading zeros removed, so it's not a very complicated task to do really. But anyway, yes, so if you do use a school server, which is perfectly fine, just do not use Bobby or Sally. So use cardiac.cs.unlv.edu because Cardiac is able to deal with threads. If in case you wrote a program that causes an infinite loop in a thread that will never stop, then at least Cardiac will be able to sort of end that thread. And your own computer will be able to as well. So your Mac or your PC or even Linux machine can easily do that. But Sally and Bobby, for some reason, cannot. So it's going to destroy that server. So what's going to happen is if your thread runs forever on a Sally or Bobby server, then imagine Mr. Meeseeks going crazy basically and just sitting there, never being able to ever stop, and it will try to then destroy the server because it's getting kind of upset. So make sure. So if you're going to use, if you do have to use a school server, it's fine, but just use Cardiac. Don't use Bobby or Sally. So there's some sample output. I have the same ones here on code grade as well. So just go ahead and compare with these numbers. These are pretty big ones, so we can't store this into unsigned long, I don't think. Make sure to count it to make sure, but I think they're big enough where it will not be able to store it onto a long. Or just imagine that the numbers will get so large that you can't store it into an unsigned long is the whole idea. Here's some smaller ones you can test with, but of course, the idea is it can get very big. So written portion, of course, you have written portion for this assignment. So answer these questions. So what system do you use? Also, maybe just sort of explain kind of the your algorithm, I guess. No, so number 1, number 2 can be any size. It won't always be that. So number 2 could be smaller. There's no guarantee. So I had it like this, but yeah, there's no guarantee for that. So just sort of answer these questions. So these ones really kind of, I think there's really no way to get these questions wrong. They're just sort of, these are not really right or wrong answers. I mean, what system do you use? And also explain your algorithm. So just kind of talk about it, how it actually worked. Does parallelization speed up the problem? Does adding more threads always cause speed up? I mean, well, we know there's certain parts of our program that's kind of can be done in sequence, so we already know that we know the answer here already. And which parts can be paralyzed, which parts are not paralyzed, but can we paralyze certain parts that are not paralyzable, or certain parts that we don't have in this program as paralyzed? Could we do that in parallel? Can we do that in parallel? So, for example, the adding part, could addition be done in parallel? That's more just kind of a brainstorm question. So there's no way you can get these questions really wrong. It's just sort of, these are more just kind of it's like an English 101 essay or paper, kind of. We're not really like it's like maybe like one page at most you have to do for this write up, but it's like an English essay. It's, kind of like, it's sort of like equivalent to how does threads make you feel? There, English 101. Yeah. So, yep, that's that. So it's due for now next Monday. And of course, that's plenty of time. So we'll see how that works out. But for now, it's due next Monday. We'll see how everything works out. So, any other questions on this? Go ahead and save this so I can upload this as well, since I do have some notes written here, which I don't know, maybe it'll help. So I'll just go ahead and I'll just save this. All right. So I guess now I'm going to go over the next sort of topic, since I do have about 20 minutes or so left. I'm trying to like keep up with the afternoon class, although I don't know why. Somehow that class goes a little faster for some reason, but at some point, we'll slow things down eventually. At least that class will slow down eventually. But anyway, we're not really too far behind now. We're not really behind in terms of materials, so we're definitely good. So nothing wrong there. So anyway, in terms of notes, so last time I went over, I guess, threading, and I went over quick sort last time. So anyway, so homework assignment 3 is due at some point. I suppose I forgot the actual due date for it, but hopefully it's not causing any real problems. I mean, quick sort, insertion sort, merge sort, just follow the videos I covered on those. Just do it the same way I did it in class. The other ones involve doing L'Hopital's rule and big O notation content. Now, of course, for the one question where you have to arrange the functions from smallest to largest growth rate, you don't have to really show all your work as long as you get the right answer, I suppose. So you can actually, you don't have to L'Hopital's rule everything, because you can tell, for example, that n squared is going to be bigger than n. You don't have to prove that to me. You can just say, well, you can assume that because it's obvious. So you actually can do that method to kind of just sort of guesstimate which one is bigger. So you don't have to actually, do that whole entire process unless you can't distinguish between two. But the first question that has those, you want to maybe use L'Hopital's rule to sort of prove that. Let's say, for example, I believe I had where 2 to the n equals theta 3 to the n. So use L'Hopital's rule to prove or disprove that statement. So that one, you want to use that method. But then for the ordering of functions, just, you know, you'll have to really show your work on that one. All right, so next topic we'll cover is going to be binary trees. I probably won't finish this today, but it's all right though. So let's go ahead and just discuss this. So basically, we have sort of two ways to store a binary tree. So we have two ways to implement, I should say, implement a binary tree. So one way, which is going to be the way we're going to go with first, is going to be using this sort of, how should I say, node pointer um, implementation. And the other is going to be an array implementation. So we'll go over the array implementation later. There will be a data structure that uses a binary tree, but the array version is sort of simpler to maintain that structure. But in general, though, this node pointer implementation is more universal because the array version only works for certain types of situations, or not really, but um, It's not a very good implementation. Only for certain situations it's pretty good. So the node pointer will be our sort of our default case. So basically, if we want to go ahead and create a binary tree, so we have to first define it. So it'll be very similar to a linked list, but a little different. So we're going to have to create a struct type. So we could, of course, make it templated as well. Um, Actually, I'm going to not make it templated for right now. Just keep it regular. So struct bin tree node. So the class could be used as well for this, but typically for very simple data types, a struct is good enough. A class is more for more complex data types. So anyway, we'll make this binary tree a binary tree of integers. So I'm going to say um, int item, I guess. That's going to be the some data that's stored in that node. And then we'll have, well, these two pointers. So just like a linked list, really. Just going to have left, we'll have bin tree node star right, like that. So it looks actually kind of similar to a doubly linked list, except that the left and right is not going to point to a right neighbor and a left neighbor. So it's going to be a left child and a right child, actually, is how it's going to be. So a binary tree can be expressed like this. So here it's going to be just a high-level view of a binary tree, which we'll be using this picture more often, but I'll go over how we can actually construct this using regular sort of code. But a binary tree looks like this, really. This is how we can sort of visualize a binary tree. Let's do it like this. So each circle there is going to be a node, and a line is going to basically represent a pointer. So obviously, this node up top, circle this in green, that node has two children, this one and that one. So, and every other, this one also has two children as well, like that. And then this node right there has a right child, but left child will contain null. So in an example like this, if let's say I don't draw the actual pointer for null, that denotes that there is no child. Say null pointer, nothing is there. And this node will both of its children, so both left and right for this will contain both null, like that. We're not going to really represent all of that like this, but that's how we can actually just visualize it. So if it has no lines going down like this, that means there's no children in there. So that's a binary tree. So for a binary tree, this really models a regular, like a tree in real life. If you look outside an actual tree, it models it perfectly. So the root of a tree is always at the very top of the tree, as always. And that is how trees are. So look outside at the window, every tree has a root at the very top. That makes sense, actually. And then these bottom nodes right here, these are all going to be your leaves. So each of these will be a leaf node. And that makes sense because really that's how a tree looks like. So the bottom of the tree is going to be your leaves and the top is your root. That's really kind of how it works, actually. I can't really see why this isn't the right idea. But in reality, though, the idea is that a leaf is kind of equivalent to that tail node for a linked list, and the root is like your head pointer. So you always start from the root, or start from the top, and then you kind of work your way down the binary tree. And the nodes that have no children are your leaf nodes, which means it doesn't go anywhere. It can't go any further. So leaf is where the traversal will stop. So you have to maintain a root pointer always to always know where that first starting node will always be. So you have, of course, just like a linked list, you have only one starting node, but you have many sort of tail nodes or ending nodes, and a leaf is your ending node. And of course, I can put some values in here. So I'll just say 5, 3, 7, 1, 2, and 4. I can put values in there as well. So that's going to be a binary tree. So let's go over how do we actually construct a binary tree. So I'm not going to construct it all the way from top to bottom, but I'll just sort of, give you an idea for how you can actually do this. So we can go to our int main portion right here. And I'm going to construct, I guess, E537. I'll construct this. I'll sort of partially construct this tree. So you first want to create a pointer, bin tree node, star root. So for assignment 5, we're going to probably have this all in a class. So I'll have a struct, but this class will have a private member called root, but I'll do it in main right now just to kind of give us an idea for how this actually works. But the idea for this is we're going to have root. I'll draw some different color. I'll keep it in this color. Root. So I want to go ahead and build a tree. So I'm going to go ahead and first say root equals new bin tree node. So I do that, well, allocates this box, this node, and root will go ahead and point to it, just like with a linked list. And I'm going to assign, let's say I want to assign to it 5. Okay, so same idea with linked list. We just say root arrow operator item equals 5. Now also you could do this. You could say star root dot item equals 5, just like with a linked list. So the arrow operator is going to do this operation where it's going to dereference the pointer and access the member of that object the pointer points to. So root arrow item means dereference the pointer and access the item field of that node that root points to and assign 5 to it. And to be always safe, so far this node will be our root node and a leaf node. We want to set both pointers to null. Now, of course, we can reset them to something else, but just to be safe, we always want to make sure that we have our leaf nodes always cut off. Now, of course, if you want to add more to our binary tree, we always can, but just to be always safe, you're going to set them both to null for right now. So at this moment in time, this will be a root node, but also it's a leaf node. If you only have one node in our binary tree, it's, remember, just like for a linked list. If it's a doubly linked list, that one node will be the head and tail node at the same time. But I'm going to go ahead and add some nodes to this. I'm going to go ahead and say, well, I'm going to say root arrow left equals new bin tree node. So I do that, well, once again, root arrow left means I want to access that left pointer of that node that root points to. I'm going to allocate a node. So say new bin tree node, of course, is going to allocate a new node to us. And a root arrow left is going to be assigned to that node. And now I'm going to just create another pointer. Bin tree node star, I'll call this temp, I suppose, equals root. So we have a temp pointer created, and it's going to move this down here. We set it equal, so we create a temporary pointer and you assign it to root. So that means temp is going to point to the same node that root points to. And if I want to move this temp pointer to this left node, just like with linked lists, we'll just go ahead and say temp equals temp arrow left. So it moves down to that left child node. So temp will move. So temp is at the root, well, temp arrow left, it's going to reassign temp to that left side node. And now, of course, I could assign some value here. So let me see what I have above. It was 3. So I'm going to go ahead and assign 3 right there. Well, to do that, it's very simple. We just say temp arrow item equals 3, which will assign that 3 value to that item field of that node that 10 points to. So we're going to insert 3 over there, like that. And I could actually add more nodes, but I'm going to go ahead and kind of leave it like this. But then again, I'm going to, if you want, I could have said temp left equals new bin tree node, but I'm going to go ahead and just sort of cut this off. So temp arrow right, so you're going to both be set to null. Always make sure we do that, so that way we don't have, if we're traversing a binary tree, we don't go beyond the bounds of our tree and go to some, to no man's land, I guess. So anyway, there we go. If I want to add more nodes, I could. And of course, I could say root arrow right equals new bin tree node, allocate a new node to this, which I'll do is really fast right there, then I'll just sort of stop. So I could say root arrow right equals new bin tree node, which will just basically just allocate a node to the right side of this root, like this. So of course, we're going to go over maybe for an assignment for how to build this up using type of an iterative structure, not using this hard code like this. But this is sort of the idea for building up your tree and for traversing elements. I guess for traversing, we'll go over that later. But really, for right now, the whole idea of a binary tree is just, it's like a linked list, really, except that we branch off in 2 different paths. So linked list, we only have one path we can take. Now, of course, if it's doubly linked list, you can go backwards or forwards, but still, it's only one path. That linked list is our path. For binary tree, we have different paths we can take. So that's sort of the idea. So we'll go over traversals of binary trees next time, and go into all the math and everything else with it. But for right now, though, we'll stop right there. So I guess that's it for today. So take care, you guys. Stay safe. Thanks for watching. Have an awesome rest of your day. And I'll see you guys on Wednesday.